Welcome to this X News Analytical Overview. Today, we're unpacking Advanced Micro Devices' August 6, 2026 definitive agreement to acquire the AI silicon startup Taalas. Throughout this explainer, we'll be taking an evidence-based, neutral look at what this pending deal actually means for AMD's competitive position and the broader AI infrastructure market. Our goal here is to strictly separate confirmed facts from vendor claims and to objectively examine the highly specialized architecture at the center of this proposed acquisition.
Here is a quick look at our agenda. We're going to cover the pending acquisition agreement, how the tech attempts to bypass the memory wall, an evaluation of the performance claims, the trade-off between specialization and flexibility, potential deployment scenarios, and finally, what to watch next.
Starting with Section 1, the pending acquisition agreement, and analyzing the known facts of the transaction. The pace of development in this sector has been incredibly rapid. Taalas was only founded in late 2023 by Lubis Abajic, specifically to pursue custom silicon for AI models. To give that some competitive context, in December 2025, NVIDIA executed a non-exclusive technology licensing agreement with Grok, which is an independent inference competitor. By February of 2026, Taalas had raised a reported $169 million, bringing its total backing to roughly $219 million. And then, on August 6, 2026, AMD formally announced its definitive agreement to acquire the startup. Now, it's absolutely crucial to point out that this transaction remains subject to customary closing conditions. Right now, it's a pending agreement, not a completed integration.
Moving to Section 2, bypassing the memory wall and taking a look at Taalas's direct-to-silicon architecture.
To really understand what Taalas is trying to build, you have to understand a concept known as the memory wall. Basically, it's a thermodynamic and performance bottleneck. In traditional general-purpose computing hardware, a massive amount of energy and time is wasted simply shuttling AI model weights back and forth between external memory, like HBM or DRAM, and the actual compute cores. It's like an incredibly energy-intensive commute just to do the basic math required for AI inference.
Taalas's design philosophy tackles this by advocating for total specialization. According to the company's own materials, the model should not be simulated on a traditional computer. It is the computer, embodied in native hardware. So instead of a flexible processor meant to run arbitrary software, their approach dictates building a custom chip dedicated to one single specific AI foundation model.
You can see the difference when you compare the two. In a traditional GPU architecture, compute cores are physically separated from external memory. That setup offers incredible flexibility, but it slams right into that memory wall we just talked about. By contrast, Taalas's vendor-described architecture uses unified silicon. It physically merges storage and computation into high-density on-chip structures. By physically hard-coding a specific neural network right into the silicon itself, the design aims to entirely eliminate the need for those energy-draining external memory transfers.
That brings us to Section 3, evaluating performance claims and interrogating the HTC-1 prototype benchmarks.
Let's look at the known physical specs of the Taalas HC1 prototype. It's a massive piece of silicon. It's manufactured on a TSMC 6nm process, and the physical die measures an enormous 815 square millimeters, containing 53 billion transistors. And critically, this specific prototype chip is physically hardwired to run exactly one foundation model, which is Meta's Llama 3.18b.
Now, the headline metric provided by the vendor asserts that the HC1 achieves 17,000 tokens per second per user. At first glance, that is certainly an eye-catching throughput number for AI inference. But as always in tech reporting, a single, unverified number is never the whole story.
We have to apply some rigorous caveats to that 17,000 tokens per second claim. First and foremost, this is a vendor-run test. It hasn't been independently standardized or audited. Second, it relies on a highly specific testing environment, a 1K input and 1K output sequence length, restricted to a 2.5 kilowatt server boundary. But most critically, Taalas explicitly acknowledges that this silicon relies on aggressive 3-bit and 6-bit quantization. Essentially, the model's parameters are highly compressed, which the company admits introduces quality degradation when compared to standard GPU benchmarks. Because of that acknowledged drop in output quality, this figure simply cannot be read as a clean apples-to-apples comparison with standard GPU inference.
Moving on to Section 4, the specialization versus flexibility trade-off, which is really the core commercial decision here.
Enterprise data centers are facing a fundamental operational trade-off. With a general-purpose GPU, arbitrary programmability is very high. Your infrastructure can run whatever new software model drops tomorrow. The downside is potentially higher operational costs in terms of raw power consumption.
The Taalas approach completely flips that dynamic. Because the ASIC is physically locked to a specific base model, arbitrary programmability is extremely low. You get potential savings in operational power, but it comes with immense capital risk. If an open-source model like Llama 3.1 becomes obsolete in just 6 months, that expensive physical hardware could instantly become a stranded asset.
Taalas does push back slightly on that rigid framing. While the base foundation model is hardwired, the company claims their platform retains some limited adaptability. They state it supports configurable context window sizes and allows for fine-tuning using low-rank adapters, or LoRa's, meaning enterprises could theoretically still specialize the model for their proprietary data. Plus, Taalas claims they can execute a 2-month cycle to translate a completely unseen software model into custom physical silicon. However, we have to note that this 2-month cadence is strictly a vendor claim, and it remains completely unproven at mass commercial scale.
So, where does AMD fit into all this? According to their official statements, AMD's intent is to build a dual-lane accelerator roadmap. They plan to integrate Taalas to create system-level inference solutions that will sit right alongside their general-purpose Instinct GPUs. From a strategic perspective, this lets AMD offer standard GPUs for flexible workloads and training, while simultaneously offering specialized Taalas silicon to customers who run highly repetitive, static inference tasks where power efficiency trumps model flexibility. But we must reiterate, this is stated intent for a future roadmap, not an integration that is completed today.
Let's look at Section 5, Potential Deployment Scenarios. We've mapped out 3 analytical pathways.
To be clear, these are not forecasts, but rather possible paths based on the current evidence. Scenario 1 is high-impact success. Here, AMD successfully productizes the technology, enterprises accept the model lock-in for their high-volume tasks, and they achieve real power savings, actively capturing market share from traditional GPUs. Scenario 2 is niche integration. In this path, the inability to arbitrarily update base models just proves too rigid for mainstream IT, relegating this hardware to edge deployments where models rarely change. And Scenario 3 is commercial failure. This happens if the rapid churn of open-source models outpaces the physical chip fabrication cycle, or if manufacturing costs make the chips just too expensive, rendering the whole architecture commercially unviable.
Which brings us to our final section, number 6, what to watch next and clarifying the unknowns.
The first major unknown here is manufacturing viability. In semiconductor engineering, there's a constraint known as reticle limit risk. Basically, when a single physical silicon die approaches 800 square millimeters, it pushes against the very physical limits of modern lithography tools. This generally introduces significant defect risks and lowers production yields, which in turn drives up consumer costs. Keep in mind, the Taalas HC1 die is an enormous 815 square millimeters, and Taalas has not yet publicly disclosed its actual defect or yield rates.
So moving forward, here is the strict checklist of unknowns that will ultimately dictate the future of this technology. First, regulatory approval and the actual closing status of the AMD deal. Second, independent benchmark audits. We need to see real-world throughput, and critically, we need independent measurements of the reasoning quality degradation caused by that 3-bit and 6-bit quantization. Third, we need actual disclosures on those HC1 defect yield rates to properly gauge commercial pricing. And finally, we need confirmed timelines for when or if an AMD-branded commercial product will actually hit the market.
Ultimately, this entire explainer boils down to one final pivotal question. Will potential operational power efficiency ever truly justify the immense capital risk of abandoning arbitrary software programmability in enterprise AI inference? AMD is clearly betting that for certain high-volume tasks, the answer is yes. But until those benchmarks are independently audited, the chips are successfully manufactured at scale, and the acquisition officially closes, that bet remains an unproven thesis. Keep a close eye on those yield numbers and independent tests as they emerge, because they will be the true measure of whether the memory wall can be profitably broken.